this next one. We have 13 to the 5th divided by 13 to the x, and we get 13 to the 4th. So let's rewrite that. So 13 to the 5th divided by 13 to the x equals 13 to the 4th. So it looks like we're able to simplify this expression here into 13 to the 4th. So we have to think about what x would be so that we essentially are able to transform these exponents down to 4. And there's a couple different ways to think about it, but we essentially want to cancel out one of these 13s up here. Since if we rewrote this with our basic principles, this 13 to the 5th power, we're going to put that up top, and so there's going to be 5 of those multiplied together. Now in the bottom, we don't know how many 13s there are. That's our problem, but we know that in the end, we want this to be 13 to the 4th, so we have to have 4 of these 13s left over. So since we have 5 up here, one of these has to cancel out. So we just want 13 in the bottom, because if we just have 13 down here, then this and this cancel, since we know 13 divided by 13 is just 1, and we would just have 4 left up top. So since we know we just need one of these down here, x in this case would just have to be 1. So x is 1, and once you plug in 1 here, you can see that it makes sense because it follows the rule. Since they have the same base, so you would just subtract the exponent. 5 minus 1 would give you 4. So in this case, you would put in the box x equals 1. And this one's a little bit trickier to solve, but if you, again, think it through with basic principles, you should be able to figure this out. Let's move on to another one. So this one, we're solving for x. This one's pretty similar to the one we just did. We have 11 to the x up top and 11 cubed down below. And there's a couple different ways you can approach a problem like this. You might want to just multiply each side by 11 to the 3rd so that you can isolate this term with the x in it. In fact, that's probably the easiest way to do this. So I'm going to multiply both sides by this denominator, 11 to the 3rd here. And that way on both sides, or at least on the left side, they'll cancel out. And on the right side, I'll be able to simplify this. So I have 11 to the x equals 11 squared times 11 cubed. And this is more an exercise in multiplying powers, but we have 2 11s multiplied together, and then 3 more 11s multiplied together here. So let me just write those out. But in total, you're going to have 5 of them. So we can rewrite this as 11 to the 5th. And you can see that x would have to be 5 in this case. So that's one method to solve this, and frankly, that's probably the easiest method. But the other way to approach it is thinking about how you divide powers. So we have 11 to the x over 11 cubed. So we know in the bottom, we're going to have 3 of these. And we know our answer, there's just going to be 2 11s left, but they're going to be up top. And over here, we have 11 to the x, but we don't know how many there are. But we know in the end that after our cancellations are made, we're just going to be left with 2. And nothing's going to be left in the denominator. So all of these x's in the denominator are going to get canceled out. So that's 3 right there, but then you have to have 2 more left up top. So x would have to be 5. Because if you had 5 of these 11s, 3 of them cancel, and you'd have 2 left. So that's another way to solve this problem, but honestly, it's a little bit trickier this way. So that's why I showed you this other, probably simpler method. But you can use either way to solve it. Because you can notice in both cases, we do end up with x equals 5. So let's do 2 more problems. And this one, we just want to rewrite the expression in the form a to the n. So up top, notice you have 6 of these a's multiplied together, and in the bottom, you just have 1. So you might see this problem as a to the 6th divided by a to the 1st. And we know that when they have the same base, you just subtract the exponents. So 6 minus 1 is 5. So in the box, you would put a to the 5th. But you can also see that by just making a cancellation. Since you have a divided by a, so that and that cancel. And then in the end, you're just left with 5 of these a's multiplied together. And let's do one last one. So we have 4 to the 6th divided by 4 to the x, and this would have to be 4 to the 0. So I'll rewrite it. 4 to the 6th divided by 4 to the x equals 4 to the 0 power. And remember, something to the 0 power is just 1. or there aren't any 4s multiplied together. So we have 4 to the 6th. So up top, we know that there are 6 of these 4s multiplied together. And in the bottom, we don't know how many there are. So that's what we're trying to figure out. But we know that when we make our cancellations and simplifications, that we end up with just 1, or 4 to the 0. So to get this, that means there are no 4s left. All the 4s were canceled out. So there would have to be an equal amount of 4s in the denominator as well as in the numerator. Since, let me just rewrite that, if we did have 4 of them, or I mean 6 of them, so if we did have 6 4s down here, then you can see that all of them cancel out. Those 4s, those, and then all of these here. And so they all cancel out, and we know that 4 divided by 4 is just 1. So you get 1 times 1 times 1 times 1 times 1. Or 6 1s multiplied together, which is just 1. So x has to be 6 in this case. It has to be the same exponent so that they all cancel each other out. And this also makes sense with our basic pattern that when they have the same base, you subtract the exponents. Since 6 minus 6 would give you 0. So in this box, x would be 6.